Welcome everyone to week 7 of our NPTEL-PMRF problem solving sessions for the course Electronic Theory of Solids. A brief introduction of mine. I am Akshay. I am a PhD student PMRF in the Solid State and Structure Chemistry unit. I am a PhD student PMRF in the Solid State and Structure Chemistry unit, SSCU of the Indian Institute of Science, IC Bangalore, India. I did my BTech MTech dual degree from IIT Kanpur in the Department of Material Science and Engineering, and I am an NPTEL-PMRF TA for this course. Alright, so let us start our today's session with problem number 1. Okay, let me just check if I have any shiny light. Just 1 minute. Alright, so let's start our today's session. So we will start with our first problem. So in problem number 1, what we have is the interaction energy of a magnetic moment mu in a magnetic field H vector is given by E equals to minus mu vector dot H vector equals to mu z times H, where mu z is the component of the magnetic moment in the direction of the magnetic field H vector. Alright, so we write mu z as S times mu, S times mu for electrons, spin half particles, where S is equals to plus minus 1. For electron spin half particle, where we are using S here, we are using S equals to plus minus 1. Now if the energy of n spins is given by minus mu h summation I equal 1 to n Si, then what is the partition function of n non-interacting spins Zn and free energy F? Alright, so basically in this problem, what is given to us, like we have to find the interaction energy of a magnetic moment mu with a magnetic field. Okay, so we are given it is given to us that if we have a magnetic moment mu, then the energy for that magnetic moment when it interacts with an applied magnetic field H vector, that is given as minus mu vector dot H vector, and if you did the dot product, that will be equals to mu z times H, where mu z is basically the component of the magnetic moment in the direction of the magnetic field. Alright, so that will be mu z times H. So that will be component of the magnetic field in the direction of the H vector, and here mu z is given to us as S times mu for electron. Okay, for electrons, it could be a plus half, plus, and we are taking the value as plus minus 1 here for S. And if we have n such spins, then we can just write the energy as this summation minus mu h. Alright, so then the energy is basically just given by this summation of mu h summation of I equal 1 to capital N Si, and then we have to find the partition function and the free energy for this non-interacting n spins. Alright, now so for this problem, for one spin system, so now we know that if we know the energy, so basically we know our I will write it as Z1 for one spin system. We have S is equals to, and S we have is equals to plus minus 1. This partition will be given by e to the power beta mu into h. So that will be equals to e to the power beta mu h plus e to the power minus beta mu h. Right? Okay, I guess this should be minus mu z. Yeah, this should be minus mu z. Okay, sorry about that. So this will be minus here. Some of the minus sign was found here. So because mu vector dot H vector, mu z is basically your magnetic component in the direction of the magnetic field. If your magnetic field is in, we are assuming it is in the z direction, so that the dot product will just give mu z times h, and there is a minus sign already in the energy, and that's we have in the summation as well. Alright, so a partition function we have to write, and so okay. So we are writing the partition function for this one electron system, where energy of one magnetic moment interacting with the applied magnetic field H is given by minus mu z times H, where mu z is the magnetic moment in the direction of the magnetic field. Alright, and we are taking S to be plus minus 1 here. Alright, and then the total energy for n spins that will be given by this, and with this information we have to find the partition function and the free energy. Alright, so the partition function formula first we find for one spin system, and that will be summation of s equals to plus minus e to the power beta mu h. Alright, that is e to the power, if you remember, basically partition function is the summation of e to the power whatever the energy values are, which is minus e to the power ei by kBt, and ei here is basically minus mu h. Okay, let me just write it as minus nu zh, and nu zh is given by plus minus s, and let me just write s here. Sorry about that, I forgot the s. So it will be e to the power beta mu h times s, and s has only two values we are considering, plus minus 1 for a one spin system. It will be e to the power beta mu h plus e to the power minus beta mu h. Alright, so that will give you 2 cos hyperbolic beta mu h. Alright, so okay, and just in case if someone doesn't remember, because we are going to use this thing a lot in this magnetic problems. So cos hyperbolic s is given by e to the power x plus e to the power minus x divided by 2, and sin hyperbolic x is given by e to the power x minus e to the power minus x divided by 2. So similarly, tan hyperbolic x will just be sin hyperbolic x by cos hyperbolic x, that is equals to e to the power x minus e to the power minus x upon e to the power x plus e to the power minus x, and the cot hyperbolic x, that comes as cos hyperbolic x divided by sin hyperbolic x, that is equals to e to the power x plus e to the power minus x upon e to the power x minus e to the power minus x. Alright, so we are going to use this a lot in this magnetic problem. So just a quick revision for this hyperbolic functions. Alright, now for so basically for one spin particle we have this result 2 cos hyperbolic beta nu h. So for n spin system, so our Zn will be just equals to whatever your partition function is for one spin to the power n, that is equals to 2 cos hyperbolic beta mu h all to the power n. Okay, so this is the partition function for this n spin system and non-interacting spin system. And then other thing that is asked is the free energy. So the free energy, so this is the free energy, and this was our partition function. Okay, this was our partition function for one spin system. Alright, and now the free energy we know is given by minus kBt ln of z, and we have to find it for the n particles. So Zn. So this will be equal to minus kBt ln z1, partition function for one spin to the power n. So this could be written as minus n kBt ln of partition function for one spin system only. So and that we know is 2 cos hyperbolic beta mu h. So our free energy will be equals to minus n kBt ln of 2 cos hyperbolic beta mu h. Right? So this will be our free energy. Okay. So this was our problem number 1. Any doubt in this one? So this was a simple one. We just have to find the partition function. Partition function is basically by definition, partition function is just given by summation over whatever your i's are, e to the minus ei by kBt. Alright, and if you know the partition function, okay, so first we find it for the one spin system, then whatever we got it as 2 cos hyperbolic beta mu h, and then for the n spin system it is just whatever the partition function for one spin system is to the power n, that is your partition function for n spin system. And then the free energy, that is given by this formula. So this formula is important, minus kBt ln of whatever your partition function is. Okay, and so another important formula is minus kBt ln of z, ln of your partition function. So you just have to use these two formulas for this problem, right? And then we get the answer. Alright, so let's move on to next problem, problem number 2. So assuming r square is approximately equals to e naught square, where e naught is your bore radius. Now what is the diamagnetic Morse susceptibility of atomic helium in CGS units, it is centimeter cube per mole. Alright, so to find this, so we know that the diamagnetic molar susceptibility of noble gas atoms is given by so that is given by this molar susceptibility chi molar will be given by minus ZE square upon 6mc square times Na and average of R square, where here Z is your atomic number, so where Z is basically your atomic number, and here we are talking about helium, our noble gas is helium, so Z is going to be 2. Okay, this is the atomic number. Alright, then E is our electronic charge, and it is in CGS unit, so it will be 4.8 into 10 to the power minus 10 ESU. Okay, so that is the CGS unit, because our answer is being asked in CGS unit. And here 1 coulomb, we need to know 1 coulomb is equal to 3 into 10 to the power 9 ESU. Alright, then the mass of the this is the mass of the electron. Okay, so here mass will be of the mass of the electron, 9.1 into 10 to the power minus 27 grams, and C is your speed of light, so that is just 3 into 10 to the power 10 centimeter per second. Na is your Avogadro number, which is 6.022 into 10 to the power 23 mole inverse. There is the number of particles per mole, but we need to find the molar susceptibility. Molar susceptibility that we have to form. So that's why we have Na in our formula. This total number of particles per mole, or total number of electrons, you can say, or spins. This one will be. And R is approximately A0, which is our Bohr radius, which is 0.529 into 10 to the power minus 8 centimeter. Okay, then just substitute this value. Substituting these values gives, okay, so if you put all those values, your chi molar, which molar susceptibility will come as minus 1.58 into 10 to the power minus 7 centimeter cube per mole. Right? Yeah, because the diametric molar. Yeah, so we want the diametric molar susceptibility, so that's why it's minus 1.5 and minus 7 centimeter cube per mole. Okay, so mainly you need to remember this formula for this kind of problem, that the molar, that diamagnetic molar susceptibility, it comes to this formula, minus Z square 6mc square Na times average of R square, and in this case average is given to you. Alright, any doubt in this one? So let's go to our problem number 3. So problem number 3, 1 minute, did I write the answer there? Yeah, answer is minus 1.58 into minus 7 centimeter per mole. And let me just check the formula is correct now. It is minus ZE square upon 6mc square and average of R square. Okay, so let's move on to our problem number 3. Right. So So in problem number 3, what is given is which of the following ions have J vector equals to 0 but S vector and L vector is not equals to 0, and the electronic configuration is also provided to you of the atoms is provided to you, and then you have to find it correspondingly we can find for the ions as well. So this is a simple problem of the Hund's rule. So let's just start doing this problem for different ions. And interesting, if you know J vector equals to 0, it is interesting. It happens when L and S are same for the just one before the half radius, as you might have seen in the lecture. So let's just do this problem. So first we will start with our Mn3 plus. Okay, so now for Mn3 plus, the electronic configuration okay, so the electronic configuration we can see that for manganese it is 3d54s2. For Mn3 plus, first of all, for transition metals, what happens is the when we have to make the ions, the electrons are removed from the 4s shell instead of the 3d ones. So first we remove two 4s electrons and then the one 3d electron, so the electron configuration will be 3d4. Alright. So now here we have D. For D, L will be equals to 2. So we will have Lz values plus 2, plus 1, 0, minus 1, minus 2. Alright. Now we have 4 electrons here. So first we have to, following the first Hund's rule, we have to maximize the value of S, and we can put all the 4 like it is less than half it, so we can put all of them and spin up. And then we have to follow the second Hund's rule, which is the maximizing the value of capital L, which is the summation of this Lz values. So following the second rule, we will put our spin up electrons like this, 1, 2, 3 and 4. Alright. So from here, S will be equals to 4 times of plus half, plus we have no spin 0 electrons, no spin minus half electrons, so will be 0 times that, so we will have S will be equals to 2. Now L is equals to summation of Lz, which will equal Lz for the spin up and then Lz for the spin down. So that will be equals to, you can see Lz, so this will be 0 because we don't have any spin down electrons. Alright, and this will be equals to 3 minus 1, 2 plus 1 minus 1, okay, plus 0 minus 1, that will be equals to 2. L is equals to 2 here. And now we have to find the value of Z. So we have to okay, and then we have to find the value of Z. Now since the 3D shell is less than half filled, we will have J equals to mod of L minus S, which will be 2 minus 2 equals to 0. So in this case we have J equals to 0 and L is equals to S. So for Mn3 plus, we have S equals to L equals to 2, which is not equals to 0, and J equals to 0. Okay, and that is what we want. Okay, we want J equals to 0 and SL not equals to 0. So this will be our answer. Mn3 plus is going to be one of those ions. And then B part, we have to check it for Mn4 plus. We know that if Mn3 plus is there, then Mn4 plus is not going to be that, because that J equals to 0, as we know, it comes for 3D4 cases only. And here we can see the electronic configuration. That is going to be 3D3 again. So we know the answer is not, but I will just solve it because it will give you a practice of using this Hund's rule. So hopefully, like because Hund's rule, basically if you have this kind of problem in your quiz assignments or in your final examination, hopefully you will not miss this kind of simple problems. So plus 2 plus 1 0, minus 1 and minus 2. Again you will have 3, so just put 3 according to Ohm's rule first and second. Then the spin S, that will be 3 times plus half, right, plus minus half, there will be 0. So our S value here comes as 3 by 2 L summation of Lz for the spin-ups and summation of Lz for the spin downs. We don't have any spin down electrons, and that will be equals to plus 3 here. And again, since the 3D shell is less than half filled, we will have J equals to mod of L minus S, there will be 3 minus 3 by 2, and it will be equals to 3 by 2. So for Mn 4 plus, J is not equals to 0. So this is also not our answer. So this is not our answer. Then C part. C is chromium 2 plus. So chromium, again we can see the electronic configuration is 3d5 4s1. If you have to make 2 plus, first go from 4s, there will be one electron will go on, and then from the 3d, so we will have electron configuration 3d4. We will have electronic configuration is 3d4. So for D, L plus 2, Lz equals to plus 2 plus 1 0 minus 1 minus 2. I have 4 electrons according to Ohm's first rule and second rule. Half electrons, minus half electrons. S will be 2. Okay, this is 3d4 now. So we know since it is also 3d4, it doesn't matter whether it is chromium or manganese. Basically, we just need to consider the electron configuration. So we know the answer is going to be the same as Mn3 plus. Okay, it was Mn3 plus. It also has 3d4 electrons, so it is also going to have the same answer. And this will give you 2. Now since the 3D shell is less than half filled, J will be equals to mod of L minus S equals to 0. So for Cr chromium 2 plus, S equals to L equals to 2, not equals to 0, and G is equals to 0. Correct? So this is also correct. This is also one of those ions. This is also our answer. Then D part. Again, D part is for chromium 3 plus. So the electronic configuration. That will be 3d3 now. So D L equals to 2. Lz will be equals to plus 2 plus 1 0 minus 1 and minus 2. And again you have to put 3 electrons or 3 spins. Spin up according to Ohm's first rule and second rule. So S is equals to 3 times half okay, so we will get 3 by 2 again, and again L that will be equals to 3. And now again, since the 3D shell is less than half filled, okay, we have J equals to mod of L minus S. 3 minus 3 by 2 equals to 3 by 2. So for CR3 plus J is not equals to 0, and thus CR3 plus is not our answer. Just a minute. Alright, so let's do for E part. Okay, so our next ion, that is Fe2 plus. Now electronic configuration again we have to find. Okay, so iron electronic configuration is 3d64s2. To make 2 plus, we will take the 4s electrons from there, so the electron configuration will be 3d6 for Fe2 plus. It will be 3d6. Okay, and then for D again we know L is equals to 2, so we are going to have Lz equals to plus 2 plus 1 0 minus 1 minus 2. Putting the spin up electrons, we have 6, so 1 2 3 4 5, and then according to the answer second rule, we put the spin down here. Then S is equals to 5 times plus half and 1 spin down. Okay, so that will be equals, that will give you 2. Alright, and here L equals to summation of this Lz of spin up plus Lz of spin down. So that will be equals to, for spin up this will give you 0, because if you sum up all the Lz values for the blue spins, so they will just cancel out, plus 2 plus 1 minus 1 minus 2, that will be 0. So this will give you capital L equals to 2. So here S and L are both equal, and they are non-zero as well. But let's just check if J is equals to 0 or not, because we need to find, we need J equals to 0 as well. Now since the 3D shell is more than half filled, now in this case it is more than half filled, J is equals to L plus S equals to 4. So J is not equals to 0 in this case. So for Fe2 plus, L is equals to S equals to 2, which is not equals to 0, but J is not equals to 0. So Fe2 plus is not our answer. Then Fe3 plus, okay. So the next ion that is given to us is Fe3 plus, and so the Fe3 plus electronic configuration that will be 3d5. Right, just 1 minute. Alright, so electron configuration is 3d5 now instead of 3d6. 3d6 was for Fe2 plus. For Fe3 plus, we will take one more 3d electron, so that will be 3d5. So d for d L equals to 2. So again the LZ values, that will become plus 2, plus 1, 0, minus 1, minus 2. We put the spin up electrons and we will be done with our 3d5 spin up only. So our S will be equals to 5 times plus half and 0 times minus half. So that will be equals to 5 by 2. Right, and L will be equals to summation of LZ for spin up plus summation of LZ for spin downs. Okay, and we don't have any spin downs, that will be 0. And spin up also, basically all of them summation will be 0, as you can see, plus 2 plus 1 minus 1 minus 2, the summation will be 0. Alright, and here L is not equals to S, so this is not going to be our answer. We're going to solve it completely. Now since the 3D shell is half filled, J will be equals to mod of L minus S equals to L plus S equals to basically S, because L is 0, so which is equals to 5 by 2. Now so for Fe3 plus, J is not equals to 0, and thus Fe3 plus is also not our answer. So it is also not the ion which has J equals to 0 and S and SRL not equals to 0. S equals to L but not equals to 0. And the last ion is Ni2 plus. Ni2 plus. Now for Ni2 plus, again we can see the electronic configuration 3d8 4s2. To make Ni2 plus, it will take 2 electrons from the 4s shell. So the electronic configuration is going to be 3d8. Electronic configuration, that is going to be 3d8. So for D, L is equals to 2. LZ will be equals to plus 2 plus 1 0 minus 1 minus 2. Now we have to put 8 electrons. First we will put the spin up according to Hertz's first rule. Then we will put spin down according to Hertz's second rule. Right, so our S will be equals to 5 times plus half plus 3 times minus half, that is going to be 1. So S is equals to 1, and L will be equals to summation of L plus summation of LZ for the spin downs. So that will be equals to 0 plus 3 plus 2 3. So capital L will be equals to 3. And now since the 3D shell is more than half filled, okay, so we will have J equals to L plus S equals to 3 plus 1, which will be 4. So for Ni2 plus, J is not equal to 0, so this is also not our answer. So this is also okay. So basically we have checked various things, and the conclusion that you have seen in the lecture as well. J is equals to 0. Either S and L both are 0, but if S and L are not equal to 0, then J is going to be 0 only in the case of one less than half filled. So for the 3D case, we have seen it will be the case for D4 configuration, and for the, okay, so this is just an aside. So in this kind of problem, so here I have solved it in detail, but if you have to solve in multiple choice questions, so if we have J is equals to 0 and S and L are not equals to 0, both of them, so that could happen only if we are filling this NL shell less than one half filled. So it will happen for D4 case, or F. As you know, so F3DL is just 7, so it will be F6. So if you have like D4, F6, then in those cases this is going to happen. Okay, or like P has 3, so P2 case as well, this can happen. Alright. So you just need to find the electronic configuration, and if electronic configuration is one of them, then this thing will happen. Otherwise, it's not gonna happen. If given the condition that S and S and L should be same, or and S and L should not be equal to 0. So if S and L are not equal to 0, and the electronic configuration is D4, F6, or P2 kind of, okay, then only you will have J equals to 0. Otherwise not. Alright. Any doubt in this problem? Okay, so this was a simple problem in Hund's tool, just for the practice. And the next problem, that is also from Hund's tool only. Okay, and here we have to find this. Okay, so first of all we have to find what are the ground state terms for the following ions. So some ions are given to us, 3 ions are given to us in this question. Okay, and we have to find the ground state terms, and then we also need to find the Randet G factor, for which the formula is this, and then we also need to find the effective Bohr magneton number, okay, which is the effective magnetic moment, also you can say, which is G times under root of J to J plus 1. Alright, so let's do this, and electronic configurations are given to you here. So let's start with part A. So part A, so first ion is dy3 plus. So first, as always, first we have to write the electronic configuration. So here we can see that for dy, electronic configuration is given as xenon, then 4f and 6s2. So again the same thing, instead of getting the 4f electron, we will 6s2 electrons will be taken out. So for dy3 plus, we will have 4f9 will be our electronic configuration. Now for F, L is equals to 3. Alright, so we will have Lz equals to plus 3 plus 2 plus 1, 0 minus 1 minus 2 minus 3. Now first we will start filling according to the Hund's first rule. So all spin up. So 7 of them are filled. Then spin down according to Hund's second rule. 7, 8, okay, just 2 will be there because we have 9 for F9. Alright, so your S value, S will be equals to this 7 times half plus 2 for spin down. Right, so that will be equals to 5 by 2. L will be equals to summation of Lz plus summation of Lz for spin down. Now here the summation of Lz for spin up, that will be 0 because it has filled all the subshells. So the summation we can see that will be 0. And we get only contribution only from the spin down, that will be 3 plus 2 equals to 5. Alright, and now since the 4f shell is more than half filled, okay, we will have J is equals to L plus S that will be equals to 5 plus 5 by 2, it will be 15 by 2. Alright, so first we have to write the ground state symbol. Ground state form is basically the symbol that we have to write. Okay, the ground state terms, which is basically a symbol, and the formula for this is L J into 2s plus 1, where we'll just write it with this. Yeah, we know that L equals to 0 corresponds to capital S, L equals to 1 to capital P, L equals to 2 correspond to capital D, L equals to 3 correspond to capital F, L equals to 4 correspond to capital G, and L equals to 5 correspond to capital H. Alright. Okay, and so on. Okay, it will be I, J, and so on. Then, so here, this is equals to L is given to us. L we have found it is 5. So L equals to 5, it means H. J is 15 by 2, and S we have found is 5 by 2. Alright, so it will be 5 by 2 times 2, 5 plus 1, 6. So symbol, ground state symbol will be 6H, 15 by 2. Okay, then we have to find the Range factor and the effective magnetic moment, effective Bohr magneton also you can say. So here we have S equals to 5 by 2, L equals to 5, and G equals to 15 by 2. Alright, so G, Range factor, L equals to 3 by 2 plus S into S plus 1 minus L into L plus 1 divided by 2J into J plus 1. Alright, so just put in the values. 3 by 2 plus 5 by 2, 5 by 2 plus 1 minus will be 5 times 5 plus 1 divided by 2 times 15 by 2 to 15 by 2 plus 1. Alright, so this gives us 3 by 2, and okay, so this you can check basically. So I'm just going to write a final answer. So by doing this calculation you will get 4 by 3. Okay, so your our G will be equals to 4 by 3 from here. Alright, then effective Bohr magneton or effective magnetic moment P, that will be G under root of J into J plus 1. You can say effective Bohr magneton actually, and the Bohr, so it is mu B times whatever the S value is going to be. So we are just writing the effective Bohr magneton. So writing mu B, we will have the G under root of J into J plus 1. So that will be G is we have found is 4 by 3, and J will be 15 by 2, 15 by 2 plus 1. Alright, so that will give you, if you do the calculation, it will give you approximately 10.65. Alright, so P will be equals to 10.65. Right, then next part B, which is for titanium. We have ion is titanium 3 plus. Now again for titanium the electronic configuration is 3d24s2. Again we will take, it is plus 3. First we will take the 4s electrons, so 2 4s electrons will be gone, and then 1 electron will be take from 3d. So the electron configuration will be 3d1. Configuration, so that will be 3d1. Just 1 minute, sorry about it, just 1 minute. Sorry about that. So we have 3D1 configuration here. For dl equals to 2, again our LZ value will be from plus 2, plus 1, 0, minus 1, minus 2. And we are just using Hund's first rule only. We can just fill it. Just one spin electron. So S will be equals to 1 times spinner. And then we have 0 spin down. So it will be 1 by 2. And L will be equals to summation of LZ for spinner plus summation of LZ for spin down. We don't have any spin down, so that will be equals 0. And that will be equals to plus 2. And now since the 3D shell is less than half filled, J is given by L minus S is 2 minus 1 by 2. That will be 3 by 2. So now the symbol. So the symbol again, and it is given by L2J, LG, and 2S plus 1. So that will be equals to, here capital L is 2, so that will be D, that means capital D. J is 3 by 2, and S is 1 by 2. 1 by 2 times 2 is 1 plus 1, 2. So it will be 2D 3 by 2. Okay. So now we have S, here we have S equals to half, L equals to 2, and J is equals to 3 by 2. Using these values, first we find the G, which is again 3 by 2. Again just put in the values in the formula. 3 by 2 S into S plus 1 minus L into L plus 1 divided by 2J into J plus 1. That will be 3 by 2. It will be 1 by 2 times 1 by 2 plus 1 minus 2 plus 1 divided by 2 times 3 by 2 and 3 by 2 plus 1. Alright, so if you do the calculation, we will get this will be equals to 4 by 5. So our G will be equals to 4 by 5. And then effective Bohr magneton P, that will be equals to G times under root of J into J plus 1. So that will be equals to 4 by 5 times 3 by 2 into 3 by 2 plus 1, which if you calculate comes as around 1.55. So P is equals to 1.55. Right? Okay, so and the last part of this problem, last ion that we have is Fu 3 plus. So the electronic configuration. Okay, so the electronic configuration for this will be, so for Fu the electronic configuration 4F14 5D1 6S2, and it is as plus 3 again. So first we will take the electron from the 6S1, so we take 2 electrons, and we take 1 electron from 5D1. So our electron configuration will be 4F14. Okay, so now again for F, L is equals to 3. So we will have LZ values equals to plus 3 plus 2 plus 1 0 minus 1 minus 2 minus 3. We have 14 electrons. So first we will go with Hund's first rule, and we will fill the all the subshell with spinner. Now we will start filling according to the Spin-Hund's second rule, but basically we are going to fill all the subshells. So S will be equals to 7 times plus half plus 7 times minus half. So in this case, as you can see, capital S value will be equals to 0, and L also will be equals to L also summation of rho the spin up ones Lj, then the spin down ones. So and you can see the summation will be plus 3 plus 2 plus 1 minus 1 minus 2 minus 3 for both of them. So sum all these numbers. If we sum all these numbers, that will be 0. So it will be 0. 0 plus 0 is equal to 0. Alright. So now since the 4F shell is more than half filled, J is equals to L plus S, is 0 plus 0 equals to 0. Alright. So first we have to write our ground state symbol. That is given by L, G, S plus 1. So that will be equals to, for L equals to 0, it will be capital S. J is 0 and S is also 0, so it will be 1 is 0. Okay, then we have S equals to 0, L equals to 0, and J is also equals to 0. So our Randeji factor, which is 3 by 2 S into S plus 1, minus L into L plus 1 divided by 2G into G plus 1. This is S L J are both 0. G will just be equals to 3 by 2. And then effective whole magneton, it is given by G and under root J into J plus 1, and since J is equal to 0, it will be 0, so our T is also equal to 0. Alright, so this was again a simple problem on Hund's rules. How do we basically use Hund's rule to again find the S and J values, and then using the S and J values, how we can find the ground state symbol, the Randeji factor, and Bohr magneton number. Okay. So hopefully this kind of problem you will be able to solve quite easily now. Any doubt in this problem? Okay. So let's move on to our problem number 5. Okay. So now problem number 5 is so we are given manganese is given to us, which has a atomic number 25. It forms an atomic vapor at 2000 Kelvin with vapor pressure 10 to the power 5 Pascal. Alright. Now you can consider this vapor to be an ideal gas. Now what is the paramagnetic contribution to the molar Curie susceptibility of this gas at 2000 Kelvin in CGS units we have to find. And for that we need to find the Randeji factor using Hund's rule, and all the other constant values are provided to us. So for this problem, we know that again the Curie susceptibility in this case is given by this I molar, that is equals to Avogadro, because it is molar, we will have multiplied by Avogadro number, which is the number of this electrons, number of electrons per unit wall per mole, and it will be G mu B by 3 J into J plus 1 by KBT. Okay, so this we get, this is for the paramagnetic case, so this is from the lecture itself. So just go to the lecture, and this is the common letter that has been derived. And I guess there is one problem where we will actually we will again derive this formula. Maybe. Okay, so this is just the formula that we know for the motor Curie's susceptibility for a paramagnetic system. Okay, so that is given by this, and then G mu B whole square 3 upon J to J plus 1. So now we need to find this G and the J value as well to find this susceptibility. So for this, what we are given is we are given manganese, and manganese has electronic configuration. So first we need to find out the electronic configuration. It is 3d5 4s2. Alright, and again now it is electronic 3d5 4s2, but for this 4s2, as we have seen, just we have seen the case of 4f14. Okay, we have seen the case of f14 case where the shell is completely filled. So if the shell is completely filled, then S equals to 0, L equals to 0, and J is also equals to 0 in those cases. Okay, so S, L and J will be 0 in those cases. So that will not contribute to our to this value. So we will not use it in the calculation of G as well. Okay, we will not use it in the calculation of G as well, because net J will be the net J contribution. So J, we have to calculate the J net basically, and J net will be from both of them. Okay, J from the 3D shell plus J from the 4S. Alright, and okay, so let me just write it in blue maybe. So in this kind of problem, now we don't have ions, but we have basically two shells. But basically we will find the J total. That will be equals to J from the 3D shell plus J from the 4S shell. Alright, and I know that for J from the 4S shell I can calculate it, but basically so let's just calculate it as well. But for J for 4S shell, now we know that if this L is equals to basically 0, so we will have just one LZ. Okay, and then we will have one spin up, one spin down. So capital S will be equals to plus half and minus half. That will be 0. Capital L will be 0, and thus J will also be equals to mod of L minus S in this case. L plus S in this case. It is only 1, so it will be 0 basically. Alright, so therefore J of 4S will be equals to 0. So our J total will just be equals to J of 3D. Okay, so for electronic configuration, we have if we have like more than two shells, then we will just sum whatever the J values are going to be. So J of total will be J3D plus J4S, but since 4S is completely filled, so J4S will be equals to 0. So J total will be just equals to J3D. So whatever we get the J value from this 3D shell, that is what we are going to use in this formula here. Alright. So now using this 3D configuration, now we have D L equals to 2. So again, like configuration, we have 3D5, LZ equals to again plus 2 plus 1 0 minus 1 minus 2. Okay, we have to fill according to Hund's first rule, and all the electrons are filled. So S will be equals to 5 times plus half plus 0 times minus half. That will be equals to 5 by 2, and capital M will be equals to summation of LZ for the spin up and summation of LZ for the spin down. We don't have any spin down, so that will be sorry about that. Okay. So basically we have capital L will be 0 here, and now since it is half filled, basically this is half filled, and since the 3D shell is half filled, J will be equals to L plus S or mod of L minus S, which will be equals to, because here L is basically 0, it will be equals to S, this is equals to 5 by 2. Alright. So from here we now now we have the J value, okay, and J total just is J3D whatever we have found. So this is basically going to be a J3D of the 3D shell, and J total is just that J, okay. So I can write it as J value. So we have the J value, and okay. So now we have the S value. S is also S is 5 by 2. And also like similar to J value, okay, similar to the J total value, similarly it will be the case for S total as well. So to total S spins, that will be also contribution from both 3D and 4S, and since from 3D case these are 0, so okay, these are 0, so again this will be the same for S as well, S3D plus S4S, and L2 total will be equals to L3D plus L from 4S, and since all of them are 0, therefore J4S is 0, these are 4S, 4S, S4S, okay. So basically J4S equals to S4S equals to L4S equals to 0, that's why we will have J total equals to J3D, S total is equals to S3D, L total is equals to L3D. So basically if you have two shells and one of the shell is completely filled, then its contribution to the total moment, either J, S or L, that will be 0, okay, because the S, L, J value it will be contributing to 0. So you just need to solve for the one which is unfilled case, and that will give you the total S, J and L values. So here S is equals to 5 by 2, L is equals to 0, and J is equals to 5 by 2. Alright. So first we need to find the G, and we know the formula 3 by 2 S into S plus 1 minus L into L plus 1 divided by 2J into J plus 1. Okay, so just put in the values. 5 by 2 plus 1. Now L is 0, so there will be nothing there, and again we will have the same 5 by 2 and 5 by 2 plus 1, okay, and that will be 0. Okay, so these things will just cancel out here, so what we will have is 3 by 2 plus half, that will be equal to 2. So G will be equal to 2. So we got the value of G. Now we need to find and we have the value of J as well, which is 5 by 2. So now we can find the pi molar just by just put in the values. Okay, the formula is this: Na times G. In case of G, we will just write 2 mu b whole square divided by 3 times it is J into J plus 1 divided by kBt. So it will be 5 by 2 times 5 by 2 plus 1 divided by kBt, and all this constant, okay, all these constants apply to you. T is equals to 200 Kelvin, 2000 Kelvin. Okay, so just use T equals to 2000 Kelvin, kB and all other constants are given to you. Okay, let me just write it as 2000. Okay, so just put in all the constant values, then you will find that pi molar, that will be equals to 2.187 into 10 to the power minus 3. It will be centimeter cube per mole. Okay, this is not dimensionless because we are using CGS unit. So in the coming problem we will use the SI units, and in SI units your susceptibility it comes dimensionless. but here you have to check that MB shall become a centimeter cube per mole. Alright, so just put in the values, the constant values here, and then you will get the answer. And the constant values they are provided here in the problem itself. Alright, any doubt in this problem? Okay, so let's move on to our next problem. Alright, this is problem number 6. Okay, so let's move on to problem number 6. So in problem number 6, what is given to us as the ground state 1s of the hydrogen atom is given to us. The wave function given to us 1 upon under root pi a cube times e to the power minus r by a, and where a is the Bohr radius. So we have to calculate the diamagnetic molar susceptibility for this atom using the Langevin formula. Okay, so this is the formula that we have just in one of the problem we have used. We have found the diamagnetic, but in that case it was given that r square we are just given to take r square as approximately equals to a naught square. But now in this case r naught, this r square, the average of r square, basically you have to use the average of r square if you remember the formula. Then here that is not given to us, instead a wave function is given to us. Okay, so this we have to solve now using the Langevin formula. The diamagnetic molar susceptibility is given by, so as we have seen in one of the other problems as well today, so this chi molar is given by minus ze square times Na divided by 6mc square times the average value of r square. Okay, this is the basically average, or you can say this is the expectation value of r square. So the expectation value of r square. Now, so we need to find only the expectation. So all the other stuff we know. V is equals to 1 for the hydrogen atom, E square Na and 6mc square, m is the mass of the electron here, and c is the speed of light. So all other are just constants. All we need to find is this expectation value of r square. This thing we need to find, and this we can calculate by and the wave function is given to you. So you can calculate it by this. This is basically given by psi r square psi, which is equals to integration over dr cube psi star r square psi, that will be equals to, so this will be 4 pi r square dr, so r cube could be written as 4 pi r square dr. Alright, and then we have this psi star will be equals to under 1 by under root pi a cube times e to the power minus r, because this is a real function, so psi star will be equals to psi, and we have r square under root pi a cube e to the power minus r by a. Alright, just a moment. So this we have to solve. So yeah, I'll just take out this constants 4 pi, and we have pi a cube outside, right? Then integration will be from 0 to infinity. R will go from 0 to infinity. Alright, we will have r to the power 4 e to the power minus 2 r by a dr. Okay, so this is our integral we have to solve. Now to solve this, let r by a is equals to x, and you can write dr equals to d times dx. Okay, so average of r, this expectation value of r square, that will be equals to here we will have 4 by a cube. Okay, 10 times r to the power 4 will become e to the power 4 times x to the power 4, so we will have e to the power 4 here, and this is also, x will also go from 0 to infinity. It will be x to the power 4 e to the power minus 2x, and dr will be a dx, so it will be e to the power 5 basically. Okay, so we will have e to the power 5 here, and we will have dx here. Alright, then we have to do this integral. Here we will get 4a square. Then I will use integration by parts. So from there I will get x to the power 4 e to the power minus 2x upon minus 2 from 0 to infinity, and minus minus we get plus half, integration from 0 to infinity 4x cube e to the power minus 2x dx. Okay, this time getting using integration by parts. So first what I will do, I will in first term I did the integration of e to the power minus 2x to the power minus 2x by minus 2 times x to the power 4, and then the limit from 0 to infinity minus whatever this integral is plus 1 by 2, which is e to the power minus 2x minus 1 by 2 minus 1 we get plus integration from 0 to infinity, and then the differentiation. So let me just write the integration by parts formula, just in case if someone doesn't remember. So integration by parts. Okay, so just a reminder, u dv is given by uv minus integration vd. Alright, so this is the integration by parts formula. Okay, so here I have taken dv as my this function. So this is my dv here, this is my u here, and this is my u here, and this is my dv here. So I integrated it and I differentiated this. Alright, this is my d. Alright, okay, so this is the integration by parts formula that I am using. Then continuing again, so this value you can see that it will give you 0. Okay, so this gives you 0, e to the power minus infinity will be 0, and x0 will be 0. Alright, so from here we will have, so I will get 8a square now, and then whatever I will have this integration from 0 to infinity 4x cube times e to the power minus 2x dx, and again we have to use the integration by parts, right? Again use the integration by parts. X cube e to the power minus 2x by minus 2 from 0 to infinity plus half integration from 0 to infinity 3x square e to the power minus 2x dx. Alright, again this will be 0, e to the power minus infinity will be 0, and let's put x equals to 0, it will be 0. So this term will be 0. This will give you 12a square, 12a square integration from 0 to infinity x square e to the power minus 2x dx. Again we have to do the integration by parts. So this is a long integration, but it's easy. It's an easy simple integration, but a long one. basically we want to remove this x to the power 4 here. So since this is to the power 4, we will have to use this integration by parts 4 times. So we have already applied it 2 times. Now this is the third time we are using integration by parts. So it will be x square minus 2x by minus 2 from 0 to infinity. You will get plus 2 integration from 0 to infinity 2x e to the power minus 2x dx. Right? Then again e to the power minus infinity will give you 0, and if you put x equals 0, this will be 0. So this term will be 0, and we will get from here we will get 12a square times integration from 0 to infinity x e to the power minus 2x dx. And then again we will again use integration by parts. It will be x e to the power minus 2x on minus 2 from 0 to infinity plus 1 by 2 integration from 0 to infinity e to the power minus 2x dx. Right? So now again this will be e to the power minus infinity, that will be 0, and x equals to 0, it will be 0. So we are left with 12a square times 6a square is 6a square integration from 0 to infinity e to the power minus 2x dx. Now this is a simple integral, this we can find easily. This we are doing. So it will be I will get a minus half outside e to the power minus 2x from 0 to infinity. Right, so this gives you minus 3a square. This gives you e to the power minus infinity is 0, minus e to the power 0 is 1, so it gives you 3a square. And that we expect, okay, we expect the expectation value of r square should be positive only. So it comes as 3a square. It means expectation value of r square is coming as 3a square. 3 times of a square. Right? Now here a and a, remember a is our bore radius. So earlier in the problem it was given that in one of the problem that we saw for the ideal gas we use this r square as expectation value r square as just a square. Here for hydrogen wave function was given to us, and we found the expectation value from that. So our molar diamagnetic molar susceptibility will be equals to minus Ze square times Ne divided by 6mc square times 3a square. Expectation value is 3a square now. Okay, so just put in the value. Z is equals to 1. Okay, we have that is for hydrogen. So Z is equals to 1, and all the other values are just a constant. So just put in those values, and we have already solved one problem, so you can take the values from there. The values are given here, not given. Okay, so just take the value from one of the previous problem that we solved in today's session. So if you just put in the values, you will get minus 0.237 into 10 to the power minus 6 centimeter cube per minute. Right? So this will be your diamagnetic molar susceptibility, and it is negative as well. So yeah, it is diamagnetic, and it's a small value as well. Okay, we have found the diamagnetic molar susceptibility. Okay, any doubt in this problem? Okay, no doubts. So let's move on to our problem number 7. So in problem number 7, what we have to do is show that the this Brillouin function approaches the Langevin function as j tends towards infinity, and what are the limits of the Brillouin function as j tends to half and y tends to 0. Okay. So this is the Brillouin function that we have found for the parametric case as done in the class in lectures as well. Okay, so that gives you your m divided by ms. So the for general j, so the Brillouin zone, Brillouin function which is bjy is given by bjy, that will be equals to 2j plus 1 divided by 2j cot hyperbolic 2j plus 1 divided by 2j times y minus 1 upon 2j cot hyperbolic y by 2j, right, where this y is equals to gj mu b jh divided by kbt, and where this gj is equals to 3 by 2 plus s into s plus 1 minus l into l plus 1 divided by 2j into j plus 1. Alright. Then first we have to find the limit as j tends towards infinity. So as j tends towards infinity, this 2j plus 1 will go to 2j, right? And so 2j plus 1 upon 2j, okay, where we have in here 2j plus 1 upon 2j, okay, so that will go towards 1. Alright, therefore the first term tends to cot hyperbolic 1. Okay, we have this cot hyperbolic, and okay, so we have 2j plus 1 upon 2j here, 2j plus 1 upon 2j here, and both of them will tend towards 1. So the first term here, this first term, okay, this first term, that will go towards cot hyperbolic y. Right, and the second term tends to the okay, and then the second term we have like cot hyperbolic y upon 2j. So y upon 2j is going to be a very small number. You can see that is y upon 2j. This is going to be a very small number now as j tends towards infinity. So the second term tends to the cot hyperbolic of a very small number. So we can use the series expansion we can use cot hyperbolic of x, and the expansion is 1 by x plus x by 3 minus x cubed by 45 and so on, which is valid for small x. The second term then becomes so the second term then becomes you can say so second term is minus 2j. Okay, the second term is minus 1 by 2j cot hyperbolic y upon 2j. If we do the expansion, it becomes minus 1 upon 2j upon y minus 1 upon 2j y upon 6j plus 1 upon 2j 1 by 45 y cube. There's a minus because that's why the sign has changed. 1 upon 45 y cube upon 2j whole cube and so on, and this will tend towards minus 1 by y, because here in the first term this j dependence will cancel out. Okay, 2j will cancel out, so the first term will be just minus 1 by y, and since j is tending towards infinity, all the other terms you can see there will be j in the denominator in all the other terms, so all the other terms will go to 0. So this will, second term will go to minus 1 by y as j tends to infinity. Alright, so therefore this bj of y tends to hot hyperbolic y minus 1 by y, which is equals to our Langevin function basically. Okay, as you can check as j tends towards infinity. Okay, so this is our answer. Like bjy will tend towards this formula, hot hyperbolic y minus 1 by y, as j tends towards infinity. Now as j tends towards half, this 2j plus 1 upon 2j, this will tends towards 2, alright, and 2j will tend towards 1, so at j equals to half, what we will have, you know that j equals to half, this should go to tan hyperbolic y, right, and that we are going to show now. So it will be bj of y will be equals to 2 times hot hyperbolic of 2y minus hot hyperbolic of y. Now this could be written as e to the power 2y minus e to the power minus 2y upon e to the power 2y plus e to the power minus 2y. Sorry, this will be plus and this will be minus, this hot hyperbolic, minus e to the power y plus e to the power minus y upon e to the power y minus e to the power minus y. Alright, now this you can write, okay, it is the denominator here in the first one, this I can write e to the power 2y plus e to the power minus 2y, this could be written as e to the power y plus e to the power minus y times e to the power y minus e to the power minus y. Okay, minus, I will have e to the power y plus e to the power minus y divided by e to the power y plus e to the power minus y minus e to the power minus y. Okay, so this will be written as 2 times e to the power 2y plus 2 times e to the power minus 2y minus this will become e to the power y plus e to the power minus y whole square divided by the common denominator, which will be e to the power y plus e to the power minus y times e to the power y minus e to the power minus y. Now this, if you open it, so basically that will be 2 e to the power 2y plus 2 e to the power minus 2y minus e to the power 2y plus e to the power minus 2y plus 2 times plus 2 upon denominator it will be e to the power y plus e to the power minus y times e to the power y minus e to the power minus y. So basically you will get e to the power 2y plus e to the power minus 2y minus 2 upon e to the power y to the power minus y e to the power y minus e to the power minus y. Right, now this we can write as e to the power y plus e to minus e to the power minus y whole square divided by e to the power y plus e to the power minus y and e to the power y minus e to the power minus y. Okay, so that leaves you with e to the power y minus e to the power minus 5 upon e to the power y plus e to the power minus 1. Okay, and this is basically as we have seen in the starting of the lecture, these are formulas for the hyperbolic functions, that is tan hyperbolic y. Alright, therefore bg of y where tan towards tan hyperbolic of y as j tends towards 1 by 2. Right, so this we already know. We should go to tan hyper y, and we have calculated it as well. It goes to tan hyperbolic y. Right, now as y tends towards 0. Okay, so last part was as we have to find j tends to a half, and then we also find the limit as y tends towards 0. So now as y tends towards 0, this cot hyperbolic 2j plus 1 times y upon 2j, this will tend towards 2j upon, okay, that is again by this expansion only. So since y tends towards 0, again this is the cot hyperbolic of a small number, and as we have seen here again we can do this expansion. You can do this 1 by x expansion. Okay, so you can again do this one, this expansion, and if you do this expansion, what will happen? Okay, so as y tends towards 0, okay, again this 2j plus 1 j plus 1 will be a small value. So let me just rewrite what is the formula. So for small x, again we know for small x this formula cot hyperbolic x is basically equals to cot hyperbolic x equals to 1 by x plus x by 3 minus x cubed by 4 and so on. X cubed by 45 and so on. Right, so what we have in here in bjy, we have cot hyperbolic. Okay, so in bj of y function formula we have 2j plus 1 upon 2j times y, and y tends to 0, so this and this is also a very small value then. So cot hyperbolic of 2j plus 1 y upon 2j, so that will be equals to 2j upon 2j plus 1 times y. It will be done here, plus I will have 2j plus 1 times y upon in the denominator I will have 2j times 3 right. Okay, and other value xq value we will ignore. Okay, they are going to be very small values. Okay, and also we will have okay, so one thing we will have this and dot hyperbolic. So for y tends towards 0, we will have this, and then we will have dot hyperbolic y upon 2j. Okay, that will, okay, this will tend toward this, and this will tend towards again 1 by x, which will be 2j upon y plus x by 3, which is y upon 2j times 3. Okay, so let me just check 1 minute. Right, I guess yeah, this is correct. Okay, and the other terms we will ignore. So this bj of y will be equals to 2j plus 1 upon 2j times, we will get 1, this is it will be 2j upon 2j plus 1 times y, and I will have plus 2j plus 1 plus 2j plus 1 times y divided by 2j times 3. Right, this is what we get from the first term. The second term is minus 1 upon 2j. Okay, so our Brilliant formula is this: 2j plus 1 upon 2j cot hyperbolic 2j plus 1 upon 2j y, and minus 1 upon 2j times that cot hyperbolic y upon 2j. So we will have 2j plus 1 upon 2j times 2j plus 1 upon y from this first one, plus 2j plus 1 times y upon 2j times 3, minus 1 upon 2j times 2j upon y, plus y upon 2j times 3. Alright, so bj will be going to this as y tends towards 0. So let's calculate this. So for this we will get 1 upon y. Okay, one term will give me 1 upon y, plus this will be 2j plus 1 whole square upon 3 times 2j whole square times y, minus 1 upon y, and minus y upon 2j whole square times 3. So here you can see plus 1 by y minus 1 by y cancel out. So we will have these two values. So we will have 2j plus 1. I can take, so let me just take y upon 3 times 2j whole square as common. And what we have is 2j plus 1 whole square minus 1. Okay, so that will be equals to y upon 12j square, and this will be you can use a square minus b square formula here. So it will be 2j plus 1 plus 1, and it will be 2j plus 1 minus 1. So it will be y 12j square. It will be 2j plus 2, which could be written as 2 times j plus 1, and this will be just 2j. So that gives us y upon y j plus 1 upon 3j. Alright, so it implies bj of y tends towards y times j. Is there a j? Okay, I have 2g, 2 times of j plus 1, and 2j. 1 minute. Minus b. I have 2j plus 2 here, right? Give me j plus 1. I will have 2j here. G square is there, so there should not be any. Yeah, this is correct. So it will be yg j plus 1 only upon 3j as y tends towards 0. So this will be our Brillouin function as y tends towards 0, which is y times j plus 1 upon 3j. Right? I guess I had written something wrong somewhere, but this is correct. This one is correct. Yeah. Alright. So y j plus 1 upon 3j. Okay, and so this was our problem number 7. Any doubt in this problem? Okay, so we have just taken the limits of our Brillouin function. In case of j infinity, j tends to half and y tends towards 0. Alright, so let's move on to our next problem, problem number 8. So here we have to calculate the room temperature paramagnetic susceptibility of an ideal gas in which atom has j equals to 1 and g equals to 2. Okay, so they have given a j equals to 1, g equals to 2. Okay, and nothing else is given to us, and we have to find the paramagnetic susceptibility. Alright, so now in this case, so earlier we have found this susceptibilities in CGS units, so there was some centimeter cube per mole or something. Now if we solve these problems using the constants in the SI units, then the susceptibility will be unitless. Okay, so let's work in SI unit now. For this problem, let's work in SI units and use the, and for this case use the quantum mechanical form for the paramagnetic susceptibility within the Ranglan localized moment order. So this is the name of that method that we have used. So basically, as we have found this paramagnetic susceptibility, that is given by n times g square j into j plus 1 times nu naught nu v square. So here I am multiplying this by nu naught because I am writing everything in the SI unit. So when you have to write the same susceptibility formula in the SI unit, okay, such that the susceptibility is unitless, then you have to multiply it by this mu naught, which is the magnetic permeability of your material, of vacuum, yeah, magnetic permeability. So that is just a constant, universal constant, mu naught. Okay, so you have to multiply within the formula, you have to multiply this by mu naught, and if you multiply it by mu naught in SI unit and everything, all the other constant they are also in SI unit, then your susceptibility will be unitless in this case. Okay, now so we have to find basically this, we already know this formula, right? Only in this case we are using the SI units, so we have multiplied by mu naught so that our susceptibility is unitless. Okay, it is similar to the previous one, and for this nothing is given to us regarding the atom or anything. What is given to us, what we need, basically j is given to us already, we don't no need to calculate it, as we did earlier. We calculated it using the Hund's rule. Now we don't need to calculate it. J is given to us and g is also given to us. Mu naught that you have to use, that is 4 pi into 10 to the power minus 7 h per meter mu b Bohr magneton, that is 9.274 into 10 to the power minus 24 joule per Tesla. Kb 1.380662 into 10 to the power minus 23 joule per Kelvin. And temperature, it is given as room temperature. You have to find it at room temperature, so you can take it for easy calculation, take it to be 300 Kelvin, okay, instead of 273 Kelvin, instead of 298 Kelvin. Like instead of taking room temperature 25 degrees centigrade, take it like 27 degrees centigrade, alright, so that the calculation is simpler. And here n is basically our moments of atoms per meter cube, right? So our susceptibility, that will be equals to whatever our n is times their z, what is we need we need g, small g is 2, so that should be actually 4, and then j is 1, and 1 plus 1 will be 2. So let me just don't write it right now. Okay, so that is 2 square g square times 1 into 1 plus 1, which will give you 2, times mu naught 4.8 to the power minus 7, okay, times mu b square, and mu b is 9.274 into 10 to the power minus 24 whole square, divided by 3 into 1.380662 into 10 to the power minus 23 into 300 Kelvin. Okay, 300. Okay, basically if all the constants are in SI units and you have multiplied by mu naught, then your susceptibility will be unitless. Okay. So this will be equals to 7.6465 into 10 to the power minus 32. Please check the calculation. So if there is any issue, then let me know. Or basically, I just have to put this constant to the calculation. There might be some calculation mistake that I might have done, but overall the concept is same. Okay, and here note that this in SI. Okay, yeah, let me just write it down as what I have been saying again and again. Note here that in SI units, the sky is dimensionless and mu naught is multiplied in the formula. Yes, this is mu naught. Okay, then now using the ideal gas law, okay, so basically to find the susceptibility, we need to find this capital N, and it is given to us in the formula that we have to consider it as it is for an ideal gas, so we can use the ideal gas law. So from ideal gas law, we know that PV is equals to nRT. Alright. So where N is number of moles of atoms. So here N will be equal to capital N by capital N. Capital N is what we need. Okay, and since we need this total number of atoms, so now here I will take pressure to be 1 atm, okay, which is a room temperature stuff. Okay, so room normal atmospheric pressure, which is 101325 to be exact. You can take 1 to 10 power 5 as well, but I guess in this calculation I just taken this 101325 Newton per meter square. R is equals to 8.3141 441, Joule mole inverse, Kelvin inverse. Temperature, take 300 Kelvin. Since we need per meter cube, I will take volume to be 1 meter cube, and Na is the Avogadro's number that we know as 6.022 in 10 to the power 23. So your capital N will be just equals to, which is your number of atoms per meter cube. That will be given by now this PV times Na upon KBT, since V is equals to 1 meter cube. Okay, just put in the values, then you will get capital N equals to 2.446 into 10 to the power 25. Okay, 2.446 into 10 to the power 25. Therefore, chi will be approximately equals to calculate, it will be 1.87 into 10 to the power minus 6. Okay, actually, let me just check if this capital N is correct. So it is. You can just check. Just check these values. Okay, so the answer might be a little different, but there was some calculation mistake. So just check if this value is correct. But basically the method is same. Okay, so basically you have to use this susceptibility formula. G and J are already given to you. All you need to find is capital N, which is your number of these atoms of this ideal gas per unit volume. For that, since it is an ideal gas, just use the ideal gas law. PV is equals to nRT, where N is per mole. So it will be PV Na by KBT. Volume you take 1 meter cube, so that your number of atoms are 1 meter cube, and then just multiply that by chi. Alright. The values might be a little different. There might be some calculation mistakes, so just check it. And just a note. So aside actually, so the problem is solved. This was the problem that we have to do. We just need to find this paramagnetic susceptibility for this ideal gas, considering it to be an ideal gas. But some interesting point about this problem: the provided value for J and G are in fact the values for molecular oxygen. Note that we calculated is a small and positive number. Okay, and the gaseous oxygen has a paramagnetic plus the gaseous. Okay, so this is for and it is small, and so basically we have calculated it for a paramagnetic case, so that is going to be positive automatically. It is paramagnetic susceptibility, so it is positive, and we can notice that it is a small and positive number. And so just note that the gaseous oxygen has a paramagnetic response to an applied magnetic field. Okay, and that is because of this small positive value of this susceptibility. So although it is small, it is not that small, I guess, compared to the whatever the diamagnetic term you will get. So still this oxygen gas molecules, they show paramagnetic response to the applied magnetic field, because if you read in some book, the way these electrons are filled in this molecular orbitals of these oxygen molecules, there are some unpaired electrons which lead to this values of G and capital G. Alright, so just an extra information. Any doubt in the last problem? Okay. Okay, so we are already about the end of our session today. We have one more problem. So let us solve this problem in our next session. Just a brief in case if you want to give it a shot. So I will just let's just go through this problem, but yeah, we'll solve it in the next session. So we will start our next session with this problem. So what is the problem here? You can try and give it a shot. It's not that difficult problem actually, quite a simple and interesting one. So first of all, we have to consider a model 3-dimensional lattice of spins, each with spin s equals to half. Okay, so we have a 3-dimensional space, and we have a 3-dimensional lattice which is filled of spins, and for each spin we have capital S equals to half. Now first we have to find what is the magnetic moment of each spin and what are the around values of the projection of the magnetic moment mi onto some chosen axis, say z. Okay, so we have to find the magnetic moment. So remember that for the magnetic moment, that is basically given by Ge times mu b. If S is given, then it will be given by S into S1. So this will give you the magnetic moment for each spin, where Ge, it is for electrons we are considering. So we can just consider, since not any other information is given to you, so and it is for a spin half particles. So for spin half particles, we will consider them as electrons. So this Range factor for electron, it is 2. So Ge will be 2, mu b is your whole magneton, and S value is given to you. So for each spin we can calculate this magnetic moment for each spin using this formula, and then the mi is just the it is given by using ms, that will be equals to that will be given by, so this mi, so that will be given by minus Ge times mu b times ms, where ms is equals to plus minus half. Okay, it will go from minus s to plus s. So it will go from it will have two values. It will have minus half plus half values. Alright, so using this we can find you can solve the part A easily. Okay, then next is the what is the magnetic next part is the what is the possible values of the magnetic energy of each spin. So this also we have done. So basically we have done some for in this question, whatever we have done, we have actually done in all the sessions. We have done problems, and basically this involves all the problems combined. Then it is asked in the B part, what are the possible values of the magnetic energy. So as we have seen, it is given by minus m vector dot h vector. Okay, okay, whatever your that is your energy, it will be e to power minus m vector dot h vector, and m vector dot h will be just equal to minus mi times h, as we have done in our, I guess, in the starting problem of this session today. So it is given by minus mi times h, and then mi we have two possible values depending on two ms, which are plus minus half. So accordingly you can find the possible values for the magnetic energy. Then once we have the potential, we have that, then what is asked is assuming that the spins are non-interacting, as we have done earlier as well, non-interacting case, calculate the magnetization of the lattice of spins when a magnetic field H is applied along the z-axis. Okay, so in that case, first you have to find the partition function, which we know is given by summation of e minus ei by kbt. Alright, and this ei we have calculated from here. Okay, which is minus mi times h, and mi we have calculated here. Okay, which is g times mu b times ms. Alright, and ms will be equal to plus minus half. So from there we can find the partition function first. Alright, so we can find the partition function here. And then from the partition function, we can find the average magnetization. You have to find first the magnetization per spin. That could be written by 1 by z times summation over I mi e to the power minus ei by kbt. That will give you the magnetization, average magnetization per spin. Alright. So after finding the partition function, find this, and then once you have this, then the total magnetization will be just equals to the number of spins times this average magnetization per spin, where n will be equals to your number of spins per unit volume. Okay, because magnetization is per unit volume, so this number of spins per unit volume. So that will solve your part C. Right. Then for part D, for a given part D is for a given value of field H. How does the magnetization M depend on temperature, and explain the behavior. So once you get the magnetization from here, from part C, just see how the whatever the function that you get, and then try to see what are its limits for t tends towards 0 and t tends towards infinity. And also then you have to find a numerical answer as well, like if number of spins per unit volume is given to you, then what is the value, basically if n is given to you. So as we have signed in from this part, you get the average m from your partition function, and total magnetization will be n times this average m, and this n is given to you here in the D part, n is small n is given to you. So just put it there and find your total this saturation magnetization. Okay, because saturation magnetization will be n times the so you will have the total magnetization from here. Okay, and small n is given to you. Then you have to take the limit t tends towards 0. At t tends towards 0, you will see that m will tends towards your this saturation magnetization times n. Times something. Okay, sorry, m will tend towards your saturation magnetization, which will be n times some function, and that will give you a saturation magnetization numerical value. Right. And then in the E part, what does the relationship between m and h reduce to for weak fields? So so this has been done in the lecture as well, and so you can try. You will have the formula for m. So just try to take the limit h tends towards 0 and find the value. And what is the expression for this? In case, how does it depend on in this case, and how does it depend on temperature? Calculate the numerical value of chi at room temperature. So that will be also basically we have to find after in this part as well. Again, you have to just take the limits as we have done for the Brilliant function problem, and we have to find this chi as well, and chi is basically given by m by h. Alright, to find the susceptibility, and in this case as for weak field, but you will see that it is proportional to 1 by t. So that is basically similar to what has been done in the lecture. Okay, so what has been shown, the formula that is shown in the lecture. So basically you will derive that formula here, and then the Curie's law basically, and then so what you will get here for h less than 0, that will be your Curie's law. And if you find chi and m by h, then it will be 1 by t, and then you have to just find it for a room temperature value. Alright. So this is the this was problem number 9. So because of time constraint, we are not able to solve this, but I have explained you the problem, so you can try it on your own once if you want. And in the next session we will start with this problem. Okay. Any doubt in this one? So let's end this session then. Okay. Thank you. Okay.